Hi everybody, welcome back to my channel. Today we'll be evaluating this integral that popped up on QN Cube's channel. I tried for a couple hours to try to solve that with Feynman integration, but during the process of trying to solve it that way, I found that you can actually solve this using traditional methods. So I'm going to do that as kind of a bonus video on this channel. It does not involve Feynman integration or the Leibniz rule or anything like that. You can evaluate this directly. But it doesn't look like you can at first glance. I kind of stumbled across this way. I don't think most people would see that you would be able to do that with traditional techniques. They would kind of automatically assume contour integration when you saw that. But anyway, let's get started. We'll use the DI method for integration by parts on this to start. We will take the derivative of the natural log of e to the x plus 1, and we will be integrating x over x squared plus 1 all squared. And I'm going to write this as 1/2 of 2x over x squared plus 1 all squared. That makes it easier to see that the top is the derivative, that we have the derivative. If we let u equal x squared plus 1, then we have du on the top. Okay, so this is going to give us e to the x over e to the x plus 1, and we'll put in those plus minus signs right there. And this is going to give us 1/2 of 1 over x squared plus 1. Yeah, because this will turn into 1/2 of u squared, 1 over u squared du, that's u to the negative 2. But we need a negative sign. Okay. Yeah, because this would be 1/2 of this to the negative 1. Then we would bring the negative 1 out. We'd get a negative 2, which is right here. And then we'd have the derivative with respect to x right there. So that's correct. Okay. So now what we have to do is we have to evaluate this at the bounds. And I'm not actually going to show that. It's not very difficult. Maybe I will show it. All right. So what we have is the limit as, let's see, well, our upper bound. So x goes to infinity of natural log e to the x plus 1 over, let's see, this is actually going to be negative. So we're going to have the limit as x goes to infinity of negative, all right, we're going to have a 2 on the bottom, and we're going to have an x squared plus 1. All right, did I get that right? Our upper bound is going to be this. If we evaluate this at infinity, it's going to be the limit as x goes to infinity of negative natural log e to the x plus 1 over 2 times x squared plus 1. Okay, let's take the limit as x goes to infinity. We would have the following form. We would get infinity over infinity, because e to the infinity is infinity, natural plus 1 is infinity, natural log of infinity is infinity, and then of course we have infinity on the bottom. So we need to use L'Hopital's rule on this. So using L'Hopital's rule on this, we would get the limit as x goes to infinity of, let's see, we're going to have the, we don't care about the negative 1/2, so we're going to ignore that. No, we'll put it, negative 1/2 times the limit as x goes to infinity of the derivative with respect to x of this over the derivative with respect to x of this. So the derivative with respect to x of this is going to be 1 over e to the x plus 1 times e to the x. And then we'd get over the derivative with respect to x of this thing, which is 2x. Well, let's see. Letting x go to infinity here would give us a, this plus 1 would become irrelevant right there. And then we would have e to the x over e to the x. In other words, just 1. And then we let our, don't forget our x is going to infinity, so we have 1 over infinity, which is 0. So the upper bound of this evaluation goes to 0. So we're going to have 0, and then we're going to have a minus something. So it's going to be the positive limit as x goes to negative infinity of 1/2 times natural log e to the x plus 1 over x squared plus 1. All right, letting x go to negative infinity here would give us natural log 1, so this would be 0. And letting x go to negative infinity here would give us infinity, so this is infinity. So that's 0 over infinity, which is 0. So we'll end up with 0 for both the upper and lower bounds when we do the evaluation. So this goes away. You guys probably didn't need to see that. There's a pretty simple limits to take. No difficult stuff there. The only thing you need to know is L'Hopital's rule. All right. So anyway, now what we're left with is that I is going to be equal to, let's see, negative times a negative is a positive, so we're going to get the positive integral from negative infinity to infinity of, well, let's see, we'll still have the 1/2, and we will have e to the x on the numerator, and then e to the x plus 1 times x squared plus 1 on the denominator. Then it's pretty easy to see that if you make the substitution that some new variable is equal to negative x, we'd get that I. And I'm not actually going to be switching the variables. I'm just going to be doing it directly. So I would also be equal to 1/2 the integral from infinity to negative infinity of e to the negative x over e to the negative x plus 1 times negative x squared is still just going to be x squared plus 1, and then our dx would be negative dx, but we'll use the negative to switch the bounds. Then multiplying the top and the bottom of our new expression for I by e to the x would give us 1 over e to the x plus 1. And now you'll see that we have the same bounds of integration for both expressions of I. They're both multiplied by 1/2, and we have the same denominator, so we can add them together. In other words, 2I is going to be equal to 1/2, this plus this. 2I is going to be equal to this plus this. So that's 1/2 the integral from negative infinity to infinity of e to the x plus 1 over e to the x plus 1. Those will cancel out. So we'll just be left with 1 over x squared plus 1 dx. And we know that the integral right here, that's going to evaluate to pi. So we will end up with 2I is equal to pi over 2, or I is equal to pi over 4. Well, there you go. Hope you enjoyed that.